Well, everyone should know that's been following this astro series that this is the Crescent Nebula NGC 6888. This is at the highest possible sensitivity, and I'm looking at the screen, 15 by 20 arc minutes, and we are almost getting the entire extent of the Crescent Nebula this evening. I am very impressed by that. 36-inch view? Maybe, maybe not. The key to this is I initiated the video a little early, so we're going to give it a chance, but I wanted to tell you what I have planned for tonight. We are at the highest possible settings for sensitivity and for exposure time. We're going to cover some 15 studies, actually, including the dumbbell. That I already imaged using my mystery settings last night. The goal for this evening is to be able to compare them, so I have saved snapshots of each of those that will be embedded following each of these studies tonight. Now, I have seen a 48-inch Schmidt telescope view. That was done, digitized photography using, I believe, a Palomar 48-inch Schmidt camera. If this is anywhere close to the presentation of the Schmidt camera, so this should pick up as much light as the Schmidt camera minus about 0.8 magnitudes. So if this view is anything that approximates it, we'll have a pretty good sense that we are actually able to see down to what I would consider probably somewhere around 18.5 magnitude stars. So we're going to look for that this evening. And I'll explain more about this project as we go forward, what brings me joy in doing it. Aside from looking at these wonders of the night sky, I'm also very interested in understanding and characterizing the way the equipment we use to view the night sky and to image the night sky actually does what it does and be able to predict some kind of results. So I call that real-time imaging characterization. And it's the principle of characterization that, to me, in all aspects of life, which is very, very intriguing. So I think our minute has passed. Our view is fully assembled. What we have here is NGC 6894, a planetary nebula in Cygnus. The planetary is magnitude 14.4, slightly smaller than one arc minute in size, 44 by 39 arc seconds. You've seen it before. The central star is magnitude 18.3, and I will be looking for that on the screen tomorrow, and maybe you will too. 5,400 light years distant. Good sky position at plus 30 degrees, which means we're hardly getting any loss over what we might expect if it were on the zenith. So this view is going to take a little bit of time to formulate, and as it formulates, let me explain what characterization is. In general, characterization is to look at something within the context of all your life experience, and then kind of get a sense of the properties of the thing you're looking at. For instance, this is a planetary nebula. It kind of looks like a round galaxy, but it's got a hole in the middle, so it's a donut, so it's probably not a galaxy. The next thing to look for is its behaviors. Now, we don't get a real sense of the behaviors of deep sky studies, maybe comets and planets, the moon, etc., things that change and we can see details of them. But when it comes to deep sky things, unless there's like a supernova explosion in a galaxy far, far away, we don't get much of a chance to really see something happening that's going on within it. Now, once you got the properties and behaviors of something down, the next thing to do is to begin to mesh them together so they have certain attributes. Under these circumstances, this happens. Under those circumstances, another thing happens. So properties and behaviors. And we do this all the time in life, we're just not very aware of it. We characterize our neighbors, our friends, our lovers, everything about the world. Characterization is an essential because we have to learn how to interact with things. So one of the things I've been doing over the last year plus with amateur astronomy, because I used to be an amateur astronomer at the eyepiece, I'm trying to compare what I saw at the eyepiece to what we can see using the imaging systems. So properties and behaviors lead to a set of insights into something, and we'll go on from there. What we're seeing here now, and it's quite obvious to me, is NGC 6898, a galaxy in Capricornus, magnitude 14, 1.2 by 0.7 arc minutes, spiral with a lowercase a, 255 million light years distant, and minus 10 degrees declination. Unlike our previous study, which was NGC 6894, this one is below the celestial equator. So one of the things you really, did I move and disturb it? I think I did. One of the things we want to learn about in characterizing what we can see through a telescope is how much effect the night sky has on it. I began with an original assumption that we lost about 4 magnitudes from the zenith overhead to about 10 degrees below the horizon, but last night's observations squeezed that a bit to about 3 magnitudes loss, and I was very pleased with that. So here I'll try, now this is the big issue, something you learn in characterizing. If you move around on a wooden floor with a tripod on it that isn't independent of the floor, you're going to disturb the image. And so you're going to lose some of the sensitivity of the study. Any change I make inside here, especially at 256 floods, some almost a minute and a half of image assembly time through experience, which I also characterize, it causes some problems with image presentation. I think we probably had as much time on this one as we can get, so let's move on and I'll talk some more. We're now on to NGC 6901, a galaxy in Aquila, magnitude 13.7. The reason I selected this is because it's almost edge-on. It's kind of a semi-oblate edgy-on. 1.1 by 0.4 arc minutes. Spiral with a large bar, lowercase ab, 216 million light years distant, plus 6.5 degrees. And so we should get a very good look at this one at magnitude 13.7. Let's assume that we can add, we're going to see galaxies down to magnitude 17.5, for instance, using these settings. Now, there's no guarantees about that. The sky conditions can affect it, any motion on my part, etc., etc. But anyway, let's assume that it is. That means we have about 3.3 additional magnitudes available to us as sensitivity. That 3.3 additional sensitivity basically says we should be seeing quite a bit of the galaxies extension outside of its core region. The core region of galaxies, based on characterization over about a year and so of using this, is typically 0.8 magnitudes fainter than the galaxy as a whole. So that would put it at 14.5. But since this is the edge, almost an edge-on, the edges should extend out, let's say, 2 magnitudes from each side, from 13.7. So the extensions of the spiral arms should be about 15.5 magnitude. Now galaxies go on way outside the realm of the spiral arms. The spiral arms is where most of the star formation has occurred, and then the rest of the galaxy is very faint. You can practically discount that. Well, characterize that baby right there. Anyway, outside of the galaxy. So all you're basically going to be able to see, even through a 36-inch scope, is the core and the extensions of a 13.7 magnitude galaxy. Our next galaxy is pretty deep south, minus 25 degrees. I figure we lose at least 25 degrees, 2.5 magnitudes due to the atmospheric absorption plus high thin clouds being at an angle at this location in the sky. This is NGC 6907, a galaxy in Capricornus. Brightish, magnitude 11.2, largest 3.4 by 2.6. So it's kind of a football-shaped galaxy. Spiral with a bar and a lowercase b. See if you want to look it up on the sky.live. They can explain the lowercase values. All right, so this is a rather obvious galaxy, almost in the mid-screen. Now, it's a magnitude 11.2 football shape, which means the extensions are going to be roughly 2.5 to 3 magnitudes fainter. So we're now talking about something like sub-magnitude 14 extensions. And you have to remember we've already lost a couple of magnitudes. Now we're talking about magnitude 16.5 due to sky position. The core itself should be magnitude 12, but we lost about 2.5 magnitudes, so that puts it at 14.5. I think that's a very nice view, and I probably will put up a few of the sky.live digital sky survey images so you can compare them. But you have to understand that is with photography under the perfect observatory conditions, and it's using a Schmidt camera which has a 30-degree field, or 30 arc-minute field of view. But I am very pleased with that. In fact, I'm seeing some kind of an extension to this galaxy right over here. Maybe it's a neighboring, it's got to be a neighboring galaxy. But given the fact it's 3.4 by 2.6, it conceivably could be an H2 star-forming region, but I doubt it. Anyway, that's our look at NGC 6907. I hope it seems like the image is fully formed. Now, one thing I will note, we are culminating and we're deep south, and we are getting a pretty decent background sky there, something I have not seen very much of in the past. Okay, we've now turned the Losmandy G11 Go to mount to NGC 6921, a galaxy in Vulpecula the Fox. Here we have another 13.5 magnitude galaxy, but it's an edge on 9 by 0.2, 0.9 by 0.2 arc minutes, spiral with a lowercase a, 195 million light years distant, plus almost 26 degrees. So we're not losing much more than 0.2 or 0.3 magnitude. This is almost overhead if we're losing anything whatsoever. I'm not seeing the galaxy on the screen. Remember, it's kind of small, 0.9 by 0.2 arc minutes. Look for something long and thin. The core should be brightish, there should be extensions going off to the side because they're only going to be about magnitude 15. So we should be getting a very good look at a very small galaxy. Now, in terms of characterization, one of the things you'll learn to do is create hypotheses. After you've characterized something in terms of its properties and behaviors, you don't know whether or not what you're thinking about something is true or not, or accurate, to what degree of accuracy. So what you want to do is start making hypothetical predictions about it, a priori predictions. One of mine was, from astronomical eyepiece viewing, was you lose about 4 magnitudes from the zenith down to 10 degrees of the horizon. However, we don't seem to be losing 4 magnitudes, we seem to be losing 3, which suggests to me that there's something innate about the way CCD imaging works, that it is able to gather more photons even when there's a brightish background sky. So there's a contrast element there. The problem with these imagers is you can easily get overexposure. And the overexposure typically tends to happen when sky conditions are pretty poor, or when something's particularly bright. So basically, my hypothesis about the range of being able to see at the eyepiece of 4 magnitudes has been constricted now to about 3 magnitudes, something I'm very happy to see. This is NGC 6923, a galaxy in microscopium. Magnitude 11.9, 2.6 by 1.3. So, an oblately presented galaxy, spiral with a large bar, and it has a ring. Now, it would be lovely to see a ring in this image. 124 million light years distant. However, mitigating against that ring possibly is the fact that it's almost minus 31 degrees, which puts it about 14 degrees above the southern horizon at culmination. We're not quite culminating yet. Now, one of the things we might be interested in is the history of galaxies. For the longest time, until photography and larger telescopes were introduced into dedicated observatories under very highly stable observing conditions at high altitudes, most thinking about galaxies as they were just nebulae. They were just little tiny clouds in space. We thought we only had a single galaxy, the Milky Way. Everything existed within the Milky Way, that all the nebula and all the stars and all what was understood to be clusters, because they were just groups of stars, and all the clouds in space were basically easily subsumed under the notion they were within our only galaxy. In space, the whole universe was the Milky Way galaxy. Now, once we had increased the sensitivity of our equipment, developed new methods like photography in stable conditions of the sky, now extended into space, we didn't really know that there were other, what we called island universes after they were discovered. And I'm not even sure who first came up with that hypothesis, probably Edwin Hubble, who eventually created the classification scheme that we know of today and that I read regularly when I go and give you data about these studies. So here we have NGC 6923 in microscopium. Let's watch as this image forms on the screen, also a galaxy in microscopium. NGC 6925, brighter, magnitude 11.3, and larger, 4.4 by 1.1 arc minute. Spiral with a lowercase bc, 130 million light years distant, and almost minus 32 degrees, which puts it at about 13 degrees above the southern horizon, and we haven't quite hit full ascent of this object, of this study yet, which we call culmination. All right, let's talk about this now. We are definitely seeing the extensions of this galaxy. I can see it even from where I'm sitting. It seems to have extended over maybe 2 arc minutes. Now, it's 4.4 and not 2.2, for instance, arc minutes in extension. And that's because, as I mentioned earlier, you got the core, you got the extensions, and then you have some, usually about twice the size of what you see is the invisible portion of the galaxy. Now remember, we got to the point where the hypothesis was that the Milky Way was the only galaxy in the universe. It was the whole universe. Then we discovered all these other galaxies. Then we discovered many of them were moving away from us. And the further away they were, the faster they were moving. So we had this idea of an expanding universe. So the hypothesis then became we had an explosive event that occurred at some time in the past that led to the unfolding of the universe, and based on microwave background radiation, we determined that occurred about 13.7 billion years ago. Well, there's a problem. Nobody can account for the beginning of the Big Bang. We have a causal problem. So this hypothesis of the Big Bang has been validated to a certain degree, but now there's some instabilities being revealed by the James Webb Telescope being able to look so deep. Galaxies look much more better developed several hundred million years after the Big Bang that they can account for theoretically. Aha! So now we have to come up with another hypothesis to account for that. Okay, this is the real test of whether we have a scope that's actually able to reveal light down to magnitude, let's call it, 16.5, so that would be 18. NGC 6927A is a galaxy in Delphinus, magnitude 16.5, which means its core is magnitude roughly 17.3. It is very small, 0.3 by 0.1 arc minute. So smearing out of light is not an issue here. Identifying it would be difficult because it'll look almost stellar, especially given the fact it's an elliptical galaxy of a type 6. Now a type 6 is actually a rather oblate sphere, so we should look for that. 193 million light years distant. It's plus 10 degrees above the celestial equator, which, well, we're seeing an awful lot of satellite passages, aren't we? Which basically says we're not going to lose more than 0.3 to 0.5 magnitudes due to the atmospheric conditions. And boy, I think that meteor just went right over where the galaxy may be. So I'm going to let this run for a while and explain something. So the prevailing theory about the universe early on when they discovered galaxies was steady state. Everything was basically where it was, although gravity in groups of clusters of galaxies was drawing things together, but everything pretty much was standing still. Then they discovered redshift. Then they determined everything's expanding. The natural result of everything expanding is they all came from a single point. The single point wasn't galaxies, it was basically some form of pure energy that turned into some form of substance that became atoms, and the atoms initially were things like the primeval atoms, hydrogen and helium with a little bit of lithium and possibly beryllium. Physicists went to work, cosmologists trying to figure out how it could be created. They determined some fateful things. They assumed that there was like this preternatural boson, which is a material substance called the Higgs boson, that the Higgs bosons gave rise to the earliest atomic nuclei. The nuclei came together. There were I'm not sure whether or not there were electrons present at the time. Probably not, because neutrons, when they decay in about 15 minutes, turn into electrons and protons, so that they probably came out of that. So the theory seemed to describe things well until we had the James Webb, and then the galaxies. They assumed galaxies didn't form, and they were quite small, maybe 1 billion years after the Big Bang. Now they're finding they're very mature, several 100 million years afterwards, and they have to rethink the entire theory. So now they have to come up with a new hypothesis. And I will explain what I think that hypothesis might be as we continue our studies of the night over these long-term exposures at 256, 44.8 flood and AGC. Okay, before we launch into how the galaxy of the universe may have come about, let's look at this globular cluster, NGC 6981. Globular cluster in Aquarius. It's also known as M72, possibly the faintest of all the Messier's globular clusters at magnitude 9.2, 5.9 arc minutes. Brightest stars are 14.2, and you can see them spread all around the globular cluster itself. Although they look a bit diffuse, I'm a little concerned about that. It's minus 12 degrees, which means we're losing about a magnitude and a half. So effectively, we're looking at a 10.5 magnitude globular cluster there, which could account for some of the spreading of the light. Now, one of the hypotheses we could have about the early universe is because globular clusters are as old as many of the galaxies that we see in space. The galaxies formed initially as globular clusters, massive globular clusters, which then created the radiational waves that went out in the cold dark matter of space, creating other stars and other stars and other stars, the cores of galaxies, whirling of the cycling in of the gravitational forces, creating the spiral arms. Many of the galaxies, however, were irregulars. They weren't actually well formed. These irregular galaxies all collided with each other, forming more stars, creating more mass, etc., etc., etc. So when looking at a globular cluster, you might want to consider the possibility that galaxies began as clusters. All right. Now, so what is possible in the universe is, and this is the breathing universe theory. It's entirely possible that there's more than one Big Bang, that they're spread all throughout what we might call the dimensions of space, although physicists would not call it space itself unless it had the ability to propagate electromagnetic radiation and for matter to take form in it. So you can imagine there's dimensions in 3 dimensions that have no 4th dimension because there's no time, nothing's changing in it. It's like an empty box. But the universe in expanding takes over more and more and more of the empty box. Now, there's 2 possibilities. Something sets an inhalation of all these galaxies so they collide again back into a Big Bang, or B, they encounter other remote, expanding Big Bang universes. And the same thing happens to these universes that happens to galaxies that begin to coalesce, and they begin to merge, and they begin to create super universes inside of a singular, unified cosmos. That's a hypothesis. Any information on it? Heck if I know. But it could account for what we're seeing now with the James Webb Space Telescope. What we're going to watch developing here is NGC 6992. It's a supernova remnant in Cygnus, otherwise known as the Eastern Veil, the brightest part of the veil. It's magnitude 7, 60 by 8 arc minutes. I think it's got an average surface brightness. I calculated it last night. I think it was somewhere around magnitude 13. 1,500 light years distant. those stars have a limited lifetime. And at the end, if they're very massive, when they go planetary, they can go nova. When they go nova, they spread shock waves of raw materials through space, and that's what we are seeing here. And that material then gets absorbed into other cold dark matter in space, creating shock waves where Bach modules form that stars coalesce out of, and whole systems. And we are now discovering planets are everywhere. There are stars that are huge, as much as 15 to 20 masses of our sun, and there are stars that are so small they basically don't have nuclear furnaces and are supergiant Jupiter-type planets. And then we have all the planets all the way down. All right. Now imagine this. Imagine our universe is this supernova remnant. It's expanding into space. What's going to happen if it were to collide with another expansionary universe? And what would happen is characterize it, make a hypothesis, think about it, come up with your own hypothesis, but never, ever, ever claim your hypothesis is a theory until you validated it through either A, coming up with a hypothesis that a notion about it that nobody knew before and then was discovered after the fact. That's called a priori mental experimentation, which is what Albert Einstein did. Or B, more data is accumulated and other scientists have an opportunity to validate the data, and then you think about it. Or ideally, you perform an experiment which affects stuff, and then you get to see the results, and that can confirm your hypothesis. And when enough people agree, you will have a theory. So as the Veil Nebula dissipates from the screen, a globular cluster should appear. NGC 7/6 globular cluster in Delphinus, magnitude 10.6, very small, 2.8 arc minutes, and if we can resolve them, we would see 15.6 magnitude stars. This is a class 1, super dense globular cluster, as dense as they get on the scale from class 1 to class XII, or 12. It is 133,000 light years distant. It lies outside the bounds of the Milky Way galaxy. This is its own miniature nucleus of a potential galaxy. The only problem it has, it doesn't have access to any more cold dark matter to continue its growth and expansion. However, were it, for instance, to collide with some other cold dark matter in space and create more stars, it could grow and multiply. One of the things we're looking for here astronomically is if we can see any of those 15.6 magnitude stars. And if we can't, we should be able to, but why not? Because the telescope just cannot resolve that. In other words, the scope, unlike the Schmidt camera, can only resolve down to about 2.5 arc seconds in size. And all the light from all those stars is just blending together, making it impossible for us to see any individual stars, except potentially further outside the bounds of the cluster. All right, we have one more study to observe tonight. Rolling on the screen now is NGC 7013, a galaxy in Cygnus, almost straight overhead. Man, this is in the best sky position possible. It's a magnitude 11.3 galaxy, 4.5 by 1.4, oblately presented spiral, lowercase a. Not very far away, 35 million light years, but not within the bounds of our own local group of galaxies. Since it is not being drawn in, it's probably got a positive redshift. It's at plus 30 degrees, so we're going to get as good a view as we possibly can get of this. We're operating at the most sensitive, highest sensitivity level of the Revolution 2 imager. We have got the exposure time set up so that it takes over a minute, probably longer, to capture the image. It's gathering photons even as I speak, and it's organizing them, hopefully correcting for any motion of my head as I'm speaking. And it is doing the best it can to pull it all together. Now, characterization. You may get it wrong. So many people get things wrong, but that's okay. At least they're thinking for themselves. Hey, if you've been following Golden Phoenix Publish, you know we've been covering the UFO phenomena. We started off in 2017 with a map of what you'd have to go through to figure out the truth of them. It's kind of a fun video. Hey, Mr. Spaceman Tune is featured. It's kind of cool. Anyway, comments are made, a map of how you have to... But the fundamental thing that's going on in our society today is people are waking up. I don't want to call it woke, because woke has more to do with prejudices and everything else. But people are beginning to think for themselves. That doesn't mean we're thinking smartly or well, but at least people are trying to think. So, when it comes to phenomena like UFO, it's not a conspiracy theory. It's a conspiracy hypothesis. Do your homework, do your research on anything you're interested in. It could be blue whales, I don't care. Make an a priori assumption about them. Maybe they're sentient. They can overwrite their instinctual responses to their environment. Whatever it is, come up with something and then look for validation. That is the key. Validation, a priori prediction, and then validation. Or if you have some control over it, if you have a UFO, please, you can perform some experiments on it to figure out how it works. Maybe Bob Lazar did, I don't know. But I don't have a UFO. I have rarely seen things in the sky, seen some things that were suspicious, but doesn't prove anything to me. Formulate a hypothesis, predict some outcomes, whatever it is, whether it's Donald Trump or Biden, whatever, the government being taken over by the deep state, whatever your hypothesis is, make some predictions, and if they come true, bump them up the probability scale. Remember, Descartes would say the only thing you can prove is that you yourself exist. Everything from there is only a probability. And I believe these galaxies and everything else are not a simulation, they're very real, with about a 99.9999% probability. Until I discover something that upsets that probability, it ain't gonna go up, but it could go down. I hope you've enjoyed this really pushing the limits of deep sky imaging tonight, along with the commentary. Practice characterization. I'm telling you, it's a great tool to have, and assume you're going to get it wrong until you get it right. Carpe Noctem.